So what I'm going to present today is joint work with Ugo Dallago from the University of Bologna. So what we are interested in this work is an automation of a worst-case runtime complexity analysis of higher-order functional programs. And the methodology that we've chosen is conceptually very simple. First, we transform the program that we're interested in by instrumenting the program with a step counter, and then we use a size type system to estimate the growth of the step counter. Now, this first step is pretty simple. Essentially, we lift all the functions into a state monad that holds the step counter, which is then sufficiently advanced. So what I would like to concentrate in this talk now is, well, this novel size type system that we propose for this kind of analysis. So in a nutshell, size types allow you to attach size information to types. So in this system, what you can then express, for instance, is that reversing a list does not increase the size of the list. Now, for our concern, such a size type system is a very nice thing because it gives us some form of modularity in our runtime analysis. However, if you look, for instance, at this very first system that was introduced now more than 20 years ago, then this system is based on a rather, well, simple type theory, I would say. So in some sense, it's limited. Nowadays, in the context, in particular in the context of termination analysis, very sophisticated size type systems exist. However, the main drawback, at least for our purposes, that in these size type systems, inference, so the thing that we are foremost interested in this work, is highly non-trivial. So how do we solve this difficulty? What we actually do is we start sort of from scratch. We start with a very simple size type system, but then we add two ingredients that we consider crucial. The one is polymorphic recursion. So in a recursively defined function, at each recursive invocation, the type of your parameters can change. And the second ingredient is arbitrary rank polymorphism. So functions can itself take polymorphic functions. And here, if I speak about polymorphism, I mean polymorphism over sizes. However, the main contribution in this talk is not the size type system itself. Rather, it's an inference procedure for such kind of size types. And we demonstrate this also in a small prototype implementation. So to keep things very simple, in the paper, we consider a very prototypical rule-based higher order programming language with eager reduction semantics. Also, we assume that these simple programs are monomorphically typed for simplicity. Now, when I speak about polymorphism here, I mean that we can quantify over sizes. So you see here, quantification refers to quantification over size indices, and these can happen possibly very deep inside a type. Then, as a second step, the declarations of constructors are set up in the way that they define a size measure. So if you look here, for instance, at the size of cons, at the size type of cons, it tells you this cons operator takes an element of size I, it takes a list of size j, and then it gives you back a list of size I plus j plus 1, where this plus 1 counts precisely the specific cons that you're using here. Then functions in this system are associated with what we call a canonical size type, and correctness of these associated types is then well enforced by a type system. Now, canonicity here essentially means that your types to the left of an error need to be annotated with distinct size variables, as you see here in these examples. So what I've depicted here is a small excerpt of the syntax-directed typing rules. Some more notable things here. Instantiation happens whenever we type a variable or a function symbol. So you see here, when we type, for instance, a variable to the left up there, which gets assigned quantified type, then we can instantiate these outermost quantifiers with the quantified variables with arbitrary size expressions. On the other hand, generalization is refined or confined to the typing of function applications. Now, when you think about it, it's usually impossible to statically derive precise sizes for your program. So what you really want to have is that your size types are approximate. And the technical tool to achieve this one is a subtyping relation. So here you see, for instance, in the rule for application, in the lower rule, we also integrate subtyping. So the argument type gets assigned a type zeta. Then you can pick a supertype for that one, and we generalize this supertype to the type that is expected by the function here. Now, subtyping in this setting essentially allows you to weaken your size indices. You see this here in the first rule that gives you this rule for the subtyping relation on base types. So what we have here, and I think you have seen something similar before, you have then such a hierarchy, for instance, of base types of increasing size. But you can also express more interesting things with this relation, for instance, that the polytype that represents a non-size increasing function is a subtype of the polytype that expresses a size increasing function, for instance. So far so good. Now, the minimum property that you would expect from such a system is subject reduction, which essentially means that types are preserved by reduction. We have also proven this for our system in the paper. And then what we get from this one is immediately our first soundness result of the size analysis, which roughly states that the sizes that you attach to your program correctly overestimate the sizes of normal forms. What we are really then interested in here is the following theorem, namely, if we manage to attach or to type the instrumented program that carries the program counter, then from the size types of the instrumented functions, we can read off and bound on the number of execution steps that you can perform in the program. So please note that this theorem then in particular also implies termination, but it gives you moreover, a bound on the number of execution steps that you can do. So what I would like to do in the remaining time of this talk is to give you some intuitions on how we now infer such size types on this very simple example, and then conclude with some examples that show the, well, strengths, but also the weaknesses of our procedure. So if you think about it, what we really want to have is now a procedure that takes such a program and attaches size expressions to these types that you see here. Now, well, depending on the strength of the language that you have at hand for expressing your size indices, this task pretty soon gets impossible. Why? Because the problem itself then gets undecidable. However, what we can hope for, and in particular also what we achieve, is some completeness result relative to the, how should I say, procedures that we use on the size index expressions. I think this will become clear in a moment. So now, as a first step towards size inferences, we compute such template types. So these template types are obtained from the types that you have in this program by attaching size indices. Whenever such a type can carry a more complex size expression, such as the return types of this auxiliary ref function or the reverse function, we introduce a fresh function symbol as a placeholder. Now, type inference then amounts to finding a concrete interpretation of these functions that we have introduced in this example, f and g for the return type of this reverse, of this auxiliary function, the reverse function. Now, to find such an interpretation, we again proceed in two steps. So the first step is what we call constraint generation. So we take our type checking system and we turn it into a system that emits constraints on the size indices. And these constraints essentially emerge from the subtyping relation where you compare the size indices of base types, for instance. In the third step, what we then do is we solve these constraints, and from this, a solution to these constraints, we can then actually reconstruct a proper typing derivation. Now the most difficult or challenging part comes actually into play when we want to implement instantiation. Why? Because whenever we instantiate a polytype to a monotype, we have a certain choice on what sizes we should use to replace, to substitute the quantified variables with. We overcome this problem by just postponing to the next state, to the solving state. So in this constraint generation step, we just introduce, whenever we substitute a size expression for a bound size variable, we just introduce a meter variable e that acts as a placeholder. So to make this a bit more concrete, let's look at this very simple example here. So if we want to type check this system, or such a program is well typed essentially when all the equations of a function adhere to the type that we have specified here. So what we will do is we will check all these equations. So now let's look at the first equation, the base case of this auxiliary reverse function. So we start with just assuming some sizes for the free variables. So let's say ys is a list that has a size n. Now with this knowledge, we can look at the type declaration of this function and actually compute an expected type. So here this expected type is drawn here. Well, the first argument is the empty list, something of size 1, and the second argument to reverse is something of size n. So we would expect the list to return a list of size f of 1 of n. Now with this knowledge, we now start to type the right-hand side of the this equation. In this case, this is very simple. Ys is a list of size n. To match this inferred type with the expected type, we simply require that this is a subtype. So this will then generate the constraint that n, the size of ys, is bounded by f of 1 of n, the size of the expected result. And we do this one for each equation. I don't want to go into details here. I just wanted to demonstrate whenever we encounter a polytype, we just replace the bound variables by this by fresh meter variables that that stand for the expressions that we want to substitute these bound variables with. And then, of course, during type checking, these meter variables will be constrained in some way. And if we continue with this one, we end up with a constraint of this shape. In this example, we end up with 9 inequalities. So now we want to solve these inequalities. What does it mean? We want to find a solution which on the one hand consists of an assignment of size indices to these meter variables that act as placeholders, and on the other hand, we want to find an interpretation for all these so far uninterpreted function symbols. And again, we proceed in 2 steps here. In the first step, we get rid of the meter variables by something that is very close to scolemization. So we represent each of these meter variables with a new size function and replace them by such scolen terms. And then in the second step, we really find a solution to these size functions. Now in these constraints, you can do a lot of simplifications. So we proceed bottom up, and then what you see, for instance, is that this S of E function should be the identity function. So we can assume this one. We can propagate this knowledge into the constraints. This gives then a trivial equation, inequality like L is less or equal to L, which we can remove, and we proceed this way until we end up with these 3 non-trivial inequalities. Now, to solve such inequalities, we essentially fix a shape of a polynomial shape, or we assume a polynomial shape of these interpretation functions, here for f, for instance, and this allows us to actually reduce these inequalities further, so that we can use a state-of-the-art SMT solver to find such interpretation functions. And we continue this way until we have solved all the constraints, which then means that this solution that you see depicted here is really a solution that makes all the initial constraints hold. And now we can go back to these template types that we have assumed before and just substitute this solution and get concrete types, size types for the initial program. So here, for instance, we get the type for reverse that we would expect. So what we then get from this one is not only a sound inference procedure, but it's also complete relative to the constraint solver, let's say, that you are using. We have implemented this one in a small prototype written itself in Haskell. Now this prototype is itself defined in terms of a bit more richer type system for the program. In particular, we allow definition of polymorphic function. We also support algebraic data types, which then allows us, for instance, to have a more refined size measure. So in this system, you can then say you have, for instance, a list of size I that holds elements of size, or that holds integers of size up to j. Now this extension is straightforward. In particular, all these ideas concerning type inference carry over to this slightly more complicated setting. So I'll use the last minute for some examples. So our prototype can actually infer this type of this size type of the reverse function that I've shown you in the beginning of my talk. And here it's also obvious to see that, for instance, polymorphic recursion is a crucial ingredient. For instance, if you look at the recursive definition of ref, right, the second argument changes in size, so in particular it also changes in type. Our prototype can also do this program instrumentation, and via this one he can derive a linear bound on the number of reduction steps of this reverse function. Our system can, of course, also deal with higher order functions. I think I will skip this one. The next function is more interesting. This is the product function. It takes two lists and computes the cross product of these two lists internally using two folds. Now, if we just want to analyze the system, actually our prototype fails. Why does it fail? To put it short, the problem is that the type of fold is too polymorphic. There is simply no room to annotate size types. So what we do here in this case is we specialize types of such higher order combinators according to this call site. And this allows us then, for instance, also to derive a relatively precise quadratic bound for the runtime of this program. So this is in another example, but since I used enough time, I think I will stop here. Thank you.